Well, thank you for all tuning in. Good afternoon. I'm delighted to welcome you all to this Electrical Energy Management Research Group seminar. And our speaker today is Professor Phil Taylor, our new Vice-Chancellor for Research and Enterprise at the university. Just to let you know that you'll see that the recording button's live, so we're planning to record this presentation. We're also aiming to take questions at the end of the talk, and we could do that either through the chat thing on the side, or perhaps we could try raising the hand icon at the end. So Phil brings with him over 25 years of experience in electrical energy systems, working in industry and academia, where he's been tackling the challenges of technology, policy, data, markets and risk for future, I think the trendy word nowadays, net zero energy networks. Currently he's co-director of the EPSRC National Centre for Energy Systems Integration, and also leader of the EPSRC Supergen Energy Networks Hub. These are exciting times for us working in research, education, electrical energy technology, with the challenges of a widespread adoption of electric propulsion, of energy networks, and how we draw these things together in terms of meeting the demand for electrical power within the constraints of our supply network, with a large amount of increased renewable energy generation, which will require significant innovation in power electronics, energy conversion, energy storage, network management. So there's a lot of stuff going on in this field. That's all very exciting for us. Equally, there's a lot of education in this area because there's a huge skills shortage in this area within the UK and across the world. And huge opportunities, I feel, both in interdisciplinary education in this area as well. So without further ado, I'm pleased to pass over to Phil, who's going to tell us about tackling the 4D energy challenge through storage and flexibility. Thank you, Phil.
Thanks very much, Phil. It's very nice to be able to come and do this talk. And thanks everyone for joining. I hope I can say a few things that are of some interest. Can you see my opening slide there okay? I'd just like to check.
Yeah.
Yeah, okay, great. So yeah, I wanted to talk really about the kind of research that I've been doing over the last, couple of decades around energy systems and the move towards net zero, as Phil said. One of the things that I would say is that a lot of the work that I do is multidisciplinary, and I work with economists, anthropologists, human geographers, geologists, just to name a few in this space. As this was an EEMG seminar at inception, I've gone for a bit more of a technical slant on the work that I cover. But if people are interested to talk about that broader interdisciplinary piece, I'm very happy to do that as well. It's something that I think is really important. Okay, so if I can advance my slide, which it doesn't want to do for some reason. There we go. So just a bit of an overview of what I was going to cover. I wanted to talk a little bit about the 4Ds, as sometimes people call them: decarbonisation, decentralisation, democratisation, and digitalisation. I started off as an electrical engineer looking at electricity grids, but in recent years it's become increasingly obvious to me that we've got to think about the whole energy system, not just electricity. BEIS for a while in the UK were obsessed that it was just all about electricity. So I want to try and debunk that a little bit. I want to cover the challenges of uncertainty and complexity in our energy system that are growing, and think a little bit about how flexibility can be used as a way of dealing with that uncertainty and complexity, and energy storage being one way of doing that. I want to then try and link this into some ideas around aggregation and control through the cloud of lots of small stochastic elements in the energy system. And then I thought I'd think with a bit of a future look at this idea that I've done some research on in the past about ideas of an autonomic energy system in the future. So a bit like the biological term autonomics. So could it be a self-healing, self-managing, self-protecting energy system? So I'm going to try and gallop through a lot of that. I'm missing lots out, so apologies, but let's have a little look, see what we can get through in the time. So first of all, some personal thoughts about the UK energy sector at the moment. What I would say is I think it's highly fragmented across many dimensions. In the UK, we privatized our energy system and then unbundled it. And we created lots of private companies that own certain aspects of the energy system. Some own the wires but can't buy or sell electricity. Some buy and sell electricity but can't own generation or wires. So it's a highly unbundled system. And that was designed based on sort of ideas of the free market economics, and that would bring competition. And at the time that did bring energy costs down, but now when we need a fully integrated approach to tackle climate change, it's causing lots of problems. And if you look at the energy system at the moment, carbon is still way too high. We have made good progress in electricity grids, but almost no progress in heat, in transport, in agriculture, land use, in aviation. So a huge job still left to do. In terms of energy costs, we've got a really strange situation where many families spend more on fizzy drinks than they do on electricity. But then we've also got around 3 million people living in fuel poverty. So a really big challenge there that needs to be tackled. Security of supply is, I guess, adequate for most customers, but some customers in remote areas are poorly served. There's a big threat on the horizon, as we know, about cyber security. So as we digitalize our energy systems, we're adding more and more vulnerabilities into the energy system. There's also another worry on the horizon, which is about climate change and severe weather events that we see, things like the beast from the east. If they get more severe and more frequent, then our security standards at the moment will not be adequate. And then there's always geopolitical events that are a worry around things like turning off the gas pipes from Russia, for example. So just a graph to try to illustrate that a bit more. If you look at this graph, this is, and I hope you can all see it okay. I guess if you're watching this on your phone, this will be impossible, but hopefully if you're on a computer, you might be able to see it. But the y-axis on this is gigawatt hours per day, and it's 2014, 15, 16, 17. And you can see that the red trace is the electricity consumption for GB in gigawatt hours per day. The blue trace is a proxy for heat demand because that's natural gas. And then the gray stepped trace you can see is transport fuels. So what we've managed to do, I suppose, in about the last 20 years is decarbonize about 40% of the red trace on that graph. So that's 40% of about 20% of our energy use. So when people get a bit carried away with renewables, it is a wonderful thing, but there's an enormous job left to do. So you can see how big transport is compared to electricity, and you can see how not just how large the gas demand is compared to electricity, but also how variable it is, which is a problem, as I'm sure you'll all appreciate. So for a while, people thought that we'd just do a bit of energy efficiency, electrify transport and electrify heat, move it all onto the grid, and then we'd be fine. Now, the problem with that, as you can see, is we'd have to build a grid with about 5 times the capacity of the one we've got now. And it's probably worth noting that in the UK alone, if we put our electricity grid end to end, it would span from here to the moon and back. So we're talking there about building a grid 5 times the capacity of the one we've got now, of that kind of scale. So very expensive, and we couldn't build it in time to avoid climate change catastrophe. So that's why we've got to look for smart grid technologies, flexibility, AI, storage, and all the kind of breakthroughs that I think everyone here is working on together. So as I said, I think we've got to look at whole systems and multi-vector flexibility. And one of the things that's interesting at the moment is that electricity grids and gas grids, for example, are run as quite separate entities owned by separate private companies on the whole, certainly at the distribution level. And we've got, on the one hand, electrical networks that are becoming congested and can't cope with the levels of renewable energy that we've got. whilst you've then got gas grids sitting here separate that don't really know how to decarbonize. So one of the things we're doing is simultaneously using methane, producing emissions, and paying money to turn renewable energy off. We're spending millions of pounds switching renewable energy off. So if we could link those two systems together more effectively, we could take the excess energy from the renewables, drive electrolyzers, produce hydrogen, and blend that into the gas grid. That protects the revenue of renewable generators, protects the electrical network, and starts to decarbonize the gas grid. It's worth also saying that people are doing a lot of work on electrical energy storage, but the gas network is inherently a huge battery. It's got gigawatt hours of storage in it, in the line pack, in the pipes, but we don't use that at the moment. Another idea is around dual fuel appliances. So you could do demand side response that is not time limited and hop from one fuel to the other. I've got some slides here that try to illustrate that. And there's on a number of these slides, you'll see references to journal papers at the bottom that you can read if you want more info. This comes from a bit of work that we did where we've modeled gas and electricity networks and modeled the couplings between them. And we started to say, well, look, this is the kind of typical system we have at the moment, an electrical and a gas system coupled sometimes through CHP, but fairly separate. And you can get the Jacobian matrix that you can see there in the bottom that shows you the electrical terms in the top, in the bottom right, the gas terms in the top left, and the coupling terms between the gas and electricity networks circled in red. And what you can do is you can start to look at, well, what happens if one of the lines between the wind farm and the grid breaks? Means that we would normally have to either switch off the wind farm or constrain it and turn it down. What if instead of doing that, we drive an electrolyzer and blend that hydrogen? And there's another paper there you can look at. Now, this is actually a project that we're working on for real, and we will be blending hydrogen into the gas grid in Gateshead this calendar year, if not this calendar year, very early next calendar year. So this isn't a pie in the sky idea, it's actually practically achievable. So if we move on now to electrical energy storage, the way that we've tended to work on electrical energy storage in my peer group is that we start off by thinking, okay, because we're systems engineers, we start off by thinking, what are the services that the energy system needs from energy storage, and how do we characterize those services, and how might we stack them? So we stack multiple services from a storage device to maximize the revenue. And then we think, right, once we've got that and we understand that duty that we're going to require from it, we can then do sizing and technology selection for the storage device. We then start working with power electronics experts like Phil Meller and the team, and with material scientists who understand energy storage materials to do end-to-end modeling. I'll show you a bit of that in a moment. We then also build grid scale facilities and do storage emulation with real-time digital simulators and digital twins, and then put cloud platforms on top of that so that you can control fleets of these devices distributed throughout the UK. So just to give you a little snapshot of some of the things we do, this is one use of the tools that we've developed where we can do probabilistic analysis based on a bundle of services. In this case, the bundle of services, one is to remove a constraint on the overhead line that's connecting this wind farm, whilst also playing games in the store market. That's the short-term operating reserve market. So we've got one storage device earning money from the store market and making sure the wind farm doesn't overload the overhead line. And through this probabilistic analysis, you can look at what the state of charge range is likely to be for this device, how many cycles it's going to have, how deep the cycling is, what kind of utilization levels, energy throughput, and important for industry, what kind of annual revenue might they be able to expect. And this tool we've got allows us to take all sorts of different multiples of services and assess them for different technologies. So as I said, what we also did was we worked with Imperial College on a materials-based model for lithium-ion batteries. We worked with Oxford University on a detailed power or relatively detailed power converter model. And then we linked all of that in one simulation environment with a network model. We were able to look at the markets and work back to services, then into the converter, and then into the storage device. And what that allows you to do is do the systems analysis, but also know what temperature the semiconductors are in the power converter and know what the degradation is that you're causing to the battery pack. And you can see that was published in the Journal of Energy Storage a few years ago. And the kind of results you get here is that you can start to fit a surface for efficiency, power, state of charge, look at the state of health of the battery. And on the top graph there, you can see the blue graph and the dashed graph. And what that top graph is showing you is the storage device providing a service to the grid and therefore earning money. And both of those lines on that top graph earn exactly the same amount of money and provide the same service. But because they have a different floating state of charge at the beginning, the aging, the capacity loss, which you can see on the graph below, is really quite different. Now, in this simple case here, you can see that having a starting or floating state of charge that's lower reduces the degradation, so extends the life of the battery. But of course, that comes with a risk, because if you run with too low a state of charge, you might then not be able to provide the service that is required of you, and then you would get financial penalties. So this is the kind of modeling work we've done, but here's some real systems we've worked on as well. So these are real full-scale energy storage projects that we've worked with industry on to build, and we've developed the modeling and the control algorithms for these devices. So the one in the top right is quite a small device, 200 kilowatts, 200 kilowatt hours. The one in the top left is a bigger one that's 2.5 MVA and 5 megawatt hours. And the one on the bottom is the biggest one in Leighton Buzzard, and that one is 10 megawatt hours, 6 MVA. And that building you can see is actually on stilts because that is an area prone to flooding. So we had to protect the storage device. So we're doing the real world stuff as well as the modeling. Another project here I was going to talk to you about briefly is called E for Future, which is a project with Nissan, National Grid, and a number of other partners you can see there. And what we're doing here is looking at vehicle to grid. So in the previous slide, you can see that there's been a move to building larger and larger lithium-ion battery systems and connecting them to the grid. There's another school of thought that says that's nonsense. Don't do that. Just use electric vehicles. And when we've got millions of these on the road, a number of them will be plugged in and you'll be able to dispatch them to the grid to help with all the services, frequency control, renewables integration that I talked about. And so you've essentially got a huge battery that's aggregated and distributed across the UK. So we're looking at how to use cloud computing to dispatch these so that they help the grid, but they also give people enough energy to make the trips that they need to make. So it's quite a nice Innovate UK funded project. I hope I'm not galloping through this too quickly, but it's supposed to be just a bit of a short blast on the kind of things we do to provoke a bit of discussion. So now the kind of more future looking work rather than real world installations and demonstration projects. This was a consortium of universities you can see at the bottom who had this idea of the autonomic power system. And apologies, this strays into areas of computing science, so some computer scientists here today might think a lot of this is very naive, but it's about as good as we could manage as a group of predominantly engineers. So the idea was that in the future, uncertainty and complexity and decentralization would grow dramatically. This would mean that goals change over time, and so do the objectives that we need to meet in the energy system. And we felt that that complexity would become so great that traditional energy systems control techniques would become untenable. And so you would need different approaches. And the first thing we thought was, well, we probably need to divide the energy system down into zones that are tractable computationally. Grid is all still physically connected, but for control and tractability purposes, we would break it down into subzones. And this had been done quite a lot before. The novel bit here was to say, and those zones can be dynamically changed in real time when the requirements change. We then also said, well, also we think that because the grid and the energy system is going to be so changeable with all the renewables, EVs, and everything that's happening in it, you wouldn't be able to pick a single optimal algorithm to control it. The best algorithm would change during the day and at different times. So we wanted to develop algorithm selectors that could try to select the optimum algorithm as we go through the day. So I'll show you a bit of the results from this. So again, the journal papers are referenced at the bottom if anyone wants more detail. So first of all, we said, right, how could we do the zoning? So we set up some criteria for zones. And what we were looking for was weakly coupled sections of the network that also had enough controllable elements within them that you could manage them and the computational intensity wasn't too great. So we looked at 4 different zoning algorithms. You can see them there: spectral clustering, fuzzy clustering, etc. And you can see on the right-hand side, each of those methods would come up with slightly different zoning decisions for how we were going to control these areas of the network. And what we wanted to explore was this useful? So we looked at the performance of these algorithms, and we saw that they could offer improved performance over current techniques, and that even in the face of 10% noise or corruption on the data, they still worked very well. But we then wanted to know, could we do it in real time? And what we looked at here was that 3 out of the 4 algorithms could do it in less than a minute, even for an energy system with more than 2,300 buses. And so we had 3 potential algorithms. The bottom graph shows that in most cases, those 3 algorithms also outperform the static zoning decisions. So this looks like real-time, on-the-fly rezoning is a useful idea, and the value of these gets greater as the networks become more and more complex. So the next step that I showed you on that diagram was about algorithm selection, and this is based on an idea from somebody called Rice in 1976, who defined the algorithm selection problem. And the idea, as you can see here, is that a single algorithm isn't going to be the best in all cases. And therefore, if you could select from a basket of algorithms, you could get overall better performance. So we thought, right, let's test this in energy systems. So we looked at a network with renewable energy in it and congested grids. And what we were trying to do is say, let's curtail the generation as small by a small amount as possible, and let's also reduce overloads in the grid to as small as possible. So we developed a lot of network states, a lot of algorithms. We had 5 different algorithms, 4 different networks, and over 40,000 different network states that we used to train our machine learning algorithms. And then we used the algorithm selector to see if, when looking at the network state measurements, could it pick the best algorithm. And on this table here, what you can see is the best algorithm, if you were just going to pick one all the time, is a form of optimal power flow, OPF. And the performance it manages to achieve is shown there in terms of number of overloads and curtailed energy in megawatt hours. We then had 2 different types of algorithm selector, and you can see there that the algorithm selectors outperformed the individual algorithm on number of overloads, but they had to do that to a certain extent by curtailing energy a bit more. But obviously overloads need to be reduced because they can't be tolerated. You're trying to do that in a way that is optimal for curtailed energy. Now, the bottom row on that table shows you that if you had perfect knowledge, in hindsight, you could pick the best algorithm every time. That's the performance you would get. So you can see that the performance of the algorithm selector is pretty close to that perfect set of algorithm selections. So again, quite an encouraging result. So I'm almost finished. You'll be glad to know. But something I wanted to say, and I've talked to Awais and others about this work we did that we published in 2018, where we tried to do something about self-organizing. So again, autonomics, I suppose, in our definition, but thinking about cybersecurity. And so we looked at a piece of electricity network that was using demand-side management to help with voltage control, and where we had a lot of smart meters in the system. And the scenario that we invented was that we imagined somebody hacked into the smart meters and then started to hit the grid with lots of denial of service attacks through the smart meters. And what we said was, we built an architecture for the control system as a multi-agent system. And we said, what if we could self-organize the architecture of that control system in response to these cyber attacks? We developed a fuzzy decision-making system that would watch what was happening on the grid, reorganize itself to try to stop the cyber attack from crashing the voltage control system. And you can see how we linked Jade with Matt Power there in that diagram to enable us to do this work. And so I'm sure what we did here is very naive for people who are experts in cybersecurity, but this is what we did. We devised some denial of service attacks, some that were static and some that were adaptive, so a bit more sophisticated. And we hit the grid with burst attacks, continuous attacks, and sequential attacks. And we were able to crash the voltage control system and cause a blackout very, very quickly and easily with the static architecture. But then when we built our self-organizing architecture, we were able to maintain voltage control even in the face of 24% of the customer population being responsible for these types of attack. So we saw that as quite an interesting autonomic way for the grid to be self-protecting. Again, I think there's a paper there that people can look at in IEEE transactions on smart grid if they want further information. So yes, apologies, I haven't talked a great deal about the interdisciplinary work with the social sciences today, but I think it's very important to see that one of the Ds, democratization, is about people and communities being empowered to take part in the net zero transition. And in order to do that, you have to understand people and organizations, their practices, their behaviors, in order to try to understand how they can and what will interact with technology or not, and in this transition. It's also really important that we think about not just the least cost transition to net zero, but a just transition to net zero that doesn't leave certain sections behind. And in these energy systems, it's very easy to design the grid to help people with Teslas and solar panels on the roof, and then spread the costs of that out across all of society. And because in the UK, they tend to add the costs of decarbonisation to the energy bill rather than doing it through taxation, it's a very unfair way to raise the revenue to drive decarbonisation, because often people on low incomes are in rental properties that don't have insulation, and also they're locked out of buying PV or electric vehicles, for example. So they are paying disproportionately for the wealthy people to have green bling, is one kind of provocative statement that you could make. So I've got a number of comments here that you can all read, so I won't read them all out, but maybe two things I would point out here on those lists. One is, I don't think anybody knows yet how to operate very low or zero inertia electrical grids. That's a big technical challenge. And I also don't think that people have quite realized how, when we get to a situation where most of our generation is zero marginal cost generation, or close to zero marginal cost generation, i.e. an extra megawatt hour from a wind turbine doesn't cost any more because there's no fuel involved, that should mean, I think, we need to look at efficiency and losses, I suppose that's the same thing, in a very different way. So people say, well, why on earth would we convert electricity into hydrogen because of all the losses in that transition? And I would say, but if that generation is zero marginal cost and you're paying money at the moment to switch that off, then why does efficiency really matter at all? So another provocation there, maybe people can tell me where I'm wrong there. So I'll stop there. Thank you very much for your attention. It's been really nice to speak to you.
Well, thank you, Phil. That really underpinned the interdisciplinary nature of this whole problem, isn't it? The whole challenge.